Okay, this is about how, now that you understand how it's built, more or less, what is the architecture, the point is, what's the best way to program it? And we'll go through the programming environment, what it means, how we use a compiler, what variables you need to set up, how difficult or easy it's to compile this machine, to program this machine. Then you have, I'll go through some compilers. There are many compilers available. I'll go through some of them. Then I'll talk about some programming considerations, just a little about MPI. We could say a lot of things about MPI communication, but I don't want to go into too many details at this stage. Then we'll start seeing what it means to run an application. And then we move into the lab, where you actually experiment and try to run application on the x86. So, programming environment. First of all, the idea is that, yes, there are several compiler available. There are several libraries, and Adrian Tate is going to talk tomorrow about the libraries. I'll describe aprun, which is the command that you know it's used to launch jobs. PBS Pro is the batch system that's available by default on the x86 machines on CLE, but here at CSCS they have a different batch system installed, which is Slurm, and so I'll show you some differences about this. And then, yes, tomorrow I'm going to talk about the performance tools. The first message I want you to understand is that there has been put a lot of effort in the programming environment by Cray, and the idea is that the programming environment should take care of many things that you usually have to take care yourself on other environments. The idea is to make programming this machine as easy as possible. So the idea, so you basically compile, you edit your source code, whatever editor you like to use, and then you compile. Whatever is the compiler that you are using, the command that you use to compile is always ftn, if it's a Fortran program, always cc, if it's a C program, uppercase cc, if it's a C++. So even if it's PGI, with PGI you normally would use something like PGF90. This is hidden in the Cray environment, and the compiler driver you need to use is ftn, always ftn. No matter if it's gfortran or PG or PGI or PartScale or the Cray compiler itself, you always have the same command to use. And then, of course, the options, the flags, are what the proper options for your compiler are required. And you don't need to specify the libraries. You don't need to specify MPI libraries. You don't need to specify scientific libraries. You don't need to specify include files. The environment takes care of this for you. We go into details about this, but that's the point. It's simple because you don't need to care with these details. You don't need to care, again, with include files, libraries. Everything is, the environment is doing this for you. I'll show you in a moment how this happens. Then you need to edit a batch file or run an interactive in some cases. You set up information in the prologue of the batch file, for example, the name of the job and the number of nodes you need to use, and then you run the executable with aprun, and that's what you need. And as I said before, ALPS is allocating the nodes you need to use. It's sending my exe to the right compute nodes, and it's executed there, and you get the output back. This is the job, and this is how you submit the job. You sub my job.job, and it does whatever it needs to do. Okay? Now, the rest of this hour and a half, goes to understanding what's behind here. The way the details are hidden from you, it's by using the module tool. The module tool is something you use to set up an environment, to set up and define some environment variables that take care of, for example, include files, libraries, tools, compiler, and so on. So if you want to use a certain compiler, you can load with module load compiler 1, for example. And then you compile your code. Then you decide that you would rather try compiler 2, a different compiler. Then you swap, module swap compiler 1, compiler 2. So you replace compiler 1 with compiler 2. If you want to run the performance tools, you need to load the proper module, module load perf tools, and so on. And this takes care of changing a lot of things so that it's simple for you to program the machine. It's also simple for the system people because you can have multiple versions of the same compiler available at the same time. They can install all of them. And when you run, when you compile, you choose the version that you are used to use or that you know that works better. On the Cray X6, on this machine, if you issue the command module list, you show which are the modules that are loaded for you. When you log into the system, some modules are already available for you by default. So for example, by default, in this machine there is no preloaded programming environment. So when you want to compile, at least this was the case on some months ago. We can check now. Here's the situation today. But if you want to compile, you need first to load the compiler module. If you want to optimize the code for the processor that's available on this machine, which is the Magnicure, you need to load the proper module. Yes?
Just to let you know, at the moment, both of these things are, well, it is correct that there's no preloaded programming environment, but the next line, that is automatically done when you load the programming environment that you want.
Okay, so there is no compiler. You need to load the compiler.
You can load the compiler, and then automatically we load the optimized library, XTP, MC12. That's automatically loaded for you.
Maria Grazia, do you have any other batteries or pointers or something?
Which one?
Both.
Which one would you love?
None of them works. Okay. So this one, module list, is to check what modules are loaded, what are available in your session. Next command is module avail. It's what you can issue to understand which are the modules that you can possibly load. What are all the modules available on the system? And for example, if you specify module avail CCE, CCE is the name of the Cray compiler. With module avail CCE, you can look at all the versions of the Cray compiler that are available on this system. There are some commands that are useful. Grazie. Some modules that are commonly used. So for example, program environment PGI is the PGI compiler. If you want to use the PGI compiler, you need to load this module. So module load XTP MC12, this is not needed anymore because it's already automatically loaded by the programming environment module you choose. If you want to use the GNU programming environment, this is the name of the module. So if you have already loaded the PGI module, you need to swap the two modules. So module swap, programming environment PGI, programming environment GNU. Same thing if you want to use the Cray programming environment. The name of the Cray programming environment is programming environment Cray. You can, having loaded the Cray programming environment, you may want to choose a specific version of the compiler itself. So you may want to swap the CC module with a specific version that you know works for you. With MPI, we have two. You can choose between the default one, the default module, which is XTMPT, and a new module that is currently available, which is XTMPH2. There are some cases which maybe are not of interest to you, but in some specific cases, you have to load this new module for all your likely common cases, it's equivalent. But in the future, only the XT-MPH2 module will be available. Compilers. Any questions about the module? It's clear, yes?
One question. When you, for example, compile with PGI, and then the next day you load Intel and forget about that you actually compiled with Intel and running PGI and run the job, will you get into trouble because of dynamic library, search path and stuff?
Okay. The compiler module has effect when you compile. So it chooses for you, the compiler choose the environment variable for the compile and link step. So you can have a module loaded, Intel module loaded, and you can execute whatever you want, no matter how that has been built. Because the module is loaded on the login node, and the executable runs on the compute node. So there are basically two different things. As for the runtime libraries, by default, compiling on the Cray, it's static compilation. So you have the libraries in the executable itself. Okay, so I already mentioned that the compiler drivers are what is used. So when you compile a Fortran program, you always use FTN. And this is the name of the drivers for the other languages. Remember, in some cases, this can be a trouble. So remember that when you are in a cross compiling environment, mean you run the compiler on the Linux node, on the service node, on the login node, and then you generate an executable that should run on the compute node. So if you try to run the executable that you have generated on the login node, that may work or may not work. It's not the right thing to do. So when you have the executable, that is meant to be executed on the compute partition. And the right way to execute it is to use AP-run. Now, there are some configuration scripts that configure, GNU configure. And what it does, you have a set of information, and it tries to understand what's your situation. In some cases, it compiles little programs and executes that little program to verify that certain libraries, for example, are available. That may not work, because when it tries to execute that little program, it's executing a program compiled for the compute nodes on the login nodes. So you need to set things, you need to pay attention to this part. And again, don't use the standard compiler names. Don't use PGF90 and PICC, because if you do that, you are using the standard compiler, and so you are generating executables for the login node, for the system node. That executable won't work on the compute node. Now I'm going to show you information about the different programming environments. You can use the MPI man page to see all the flags, all the options available. I'm not going to go through all of them. I'm just going to underline some of the options which, to me, are useful. So for PGI programming environment, there are some options which you can use to provide feedback from the compiler. If you don't specify a listing, what the PGI compiler does is to provide you information on the interactive shell. So either you save this in a file, or you won't file that information anymore. It's not producing a listing by default. So you need to ask for a listing file with the mlist option. With minfo, you get information about the optimization that have been performed. And with -m neginfo, you get the information that Neil was mentioning before. So you get information about why the compiler wasn't able to optimize the code. The preprocessor option is mpreprocess, okay? And then you have some optimization options. To my experience, you can compile with -fast, and you get generally a good optimized code. Then there are other options. For example, this allows you to make some, force the compiler to make some interprocedural analysis and inlining some routines. And this is more aggressive, and in some cases is better. The code produces a better code, a faster code. You can control inlining by specifying how many levels of inlining the compiler should consider. Again, some other features. This is Fortran basically, so it's how is the Fortran statement, how many, if there is a limitation in the number of characters, if it's free format, if it's fixed format, and so on. In some cases, this is useful if you have a main program which is in C or C++ that is calling Fortran routines, and you are using the FTN driver to link to generate the executable. Then in this case you need this option, because otherwise it would be looking for a Fortran program module. I8 and R8 are what you need to specify if you want that integer and real variables by default are 64-bit, so 8 bytes. And byte swap IO. This is useful to automatically convert the files in big endian files. Does everybody know what big endian and little endian mean? No? Okay. This has to do with how the bytes are numbered in files. So what is byte number 0 versus byte number? If you have 64-bit variable, for example, you have 8 bytes. You can have byte number 0 on the leftmost part, and byte number 1, byte number 2, and so on. Or you can have byte 0 on the rightmost part. And so there are two conventions, right? Two standards. x86 machines are little endian, and so x86, which uses AMD processor, it's little endian. Some other machines, SGI, I think, has different standard. So this means that if you want to write a file that should be read on a system with different standard, you need to take this into consideration. So by using M-byte swap IO, you get this white swap in the input-output operations. You need to specify option -MP if you want your OpenMP directive to be recognized by the compiler. And with mconcur, you allow the compiler to do some attempt to generate parallelization in your code. So even if you don't specify OpenMP directives, it tries to identify parallel regions in the code and to apply parallelization to the code. These are just some of the options. If you want to get more information, you have to use the man pages, but you need to use the man pages for the specific compiler you are addressing. If you do man FTN, you get only the information on the driver, the compiler driver. If you want to have information about the PGI compiler, then you need to ask for man PGF90 or man PGCC and so on. There is a PGI users guide on the web, and that's it. Okay, so yes.
Maybe an off-topic question, but I'm just curious about this automatic parallelization of these PGI compilers. Does it work well?
It does what it can. I mean, of course, if you have control on what you do, it's always typically much better than this. But the point is, for example, you have hundreds of routines, and you know that there are some of them which are very important, take most of the time. Then you can work on this routine in particular and optimize the code and parallelize the code there. Then there may be some percent of the code, some potential parallelism in all the other routines, and you have no time or you don't want to look at all of them, so you can try to see what happens if you enable automatic parallelization there. Then you may gain something. But surely, if you do it yourself, in theory, in practice, that's, in my experience, is always better than the automatic parallelization. Cray compiler environment. Okay, so as some of you may know, we've been doing high-performance computers since a long time, and in the 80s we were using vector computers, and we were using our own compiler, the Cray vector machine, where the programs were generated with the Cray compiler. And when we came to the let's say the XT3 machine, we were using the AMD Opteron processor, and we were relying on commodity compilers, so PathScale compiler, PGI compiler, or the compiler that we are going to see. In 2008, we decided to get the old vector compiler and use it as a starting point to generate a compiler also for the scalar processors, also for the x86 processors, because the new chips were featuring sort of vector features. The SSE instructions were short vectors. The new AVX feature in the next generation machines, it's a vector instruction. So the expertise we had in building vector codes from the 80s is coming useful also for generating instructions on the new x86 chips. So we started this compiler in 2008, so now it's about 2 years and a half that we are using this compiler. So it's a new compiler, but there are some interesting features in this compiler already, and the quality of the code, the efficiency of the code that is generated is increasing every day. By the way, this compiler has the support, a strong support for the coarray Fortran. That's the coarray features, which is in the new Fortran standard. And there is a strong support from Cray on this compiler. Again, you need to use the module and load this module. Program environment Cray is the module for the Cray compiler. And these are some options. RA is the option that creates a listing with a lot of optimization information. And also that loop mark feature that Neil was referring to before. So for every do loops, every do loop is marked, and you have on the right side information about the kind of optimization performed on the do loop, whether it has been vectorized or unrolled or whatever. And in the listing, you get also the information about what's going on and about the quality of the compilation process. Then you have some preprocessor options. You have some optimization options. In the Cray compiler, historically, by default, you get a very high optimization level. So by default, you get -02 on the Cray compiler. You can have more aggressive optimization. Not necessarily more aggressive optimization produces faster code. Then you can control inlining and so on. Also here you have options to control the format of the Fortran statements. You can control the size of default real and integer variables. You can control also here the indiness. The difference is that in this case, this is a link time option, not a compile time option. So it applies to all the routines in the code, while in the case of PGI, it was a compile time option, so you can selectively choose which routines to compile with swapping the bytes. In this case, you can't do that. This is a link time options. All the code, all the routines will consider the byte swapping. There are other ways to control this that I show in a while. Then you have the prioritization options. By default, it recognizes the OpenMP directives. So the option is OMP, and by default, it's enabled. If you don't want OpenMP to happen, you have to specify no OMP. And then you have several levels of aggressive prioritization, means the kind of operation it performs in processing your OpenMP loops. Again, you have man pages available. Cray FTN is the name of the man page for the Cray compiler, and so on.
So,
Yes?
so the -02, -03 attacks different parts of the codes than -0 thread to -0 thread.
Yes. This is the generation of instruction, meaning the optimization level, which introduced the scalar optimization, the vector optimization, and so on. The thread here has to do only with the parallelization, the OpenMP parallelization part. So it's more aggressive in handling the variable related to the threading. Maria Grazia, avevi una domanda? No. Okay. With the Cray compiler, with the Cray programming environment, you get not only the compiler, but also some other features that may be interesting for you. For example, you get the assign command. The assign command has some historical, it's a reminder of historical things, and can be used to affect the way the I/O library, what the I/O library do. So, for example, you can specify an assign statement to some files and ask that all the output or input that goes to that files behaves according to some specific information. So, for example, if you want this swap things, the byte swap things, to be applied to a specific file, even if you have not compiled the code in that way, you can do at runtime by simply asking that, for example, assign -n swap and the name of the file, and then all the I/O performed on that file will be swapped. Okay, this applies to Fortran only. So you have ways to control what happens. So, for example, this is the case. This is an example. The file AOF, all the I/O to file AOF will be swapped. This is the effect of this assign statement. And you decide at runtime what is affected and what is not affected by this statement. So this adds some flexibility to your execution environment. You don't need to do that at link time. You can do it at runtime on the files that you think require this kind of operation. Another command that comes, and it's useful, that comes with the Cray programming environment is the explain command. So, for example, you are compiling a code and you get an error, and this is the final error you get. So you can use explain to get more information about what this FTN 2116 means. You can get the error code and issue explain FTN 2116, and you get some more information about the error. You can do the same with I/O error. You run the code, you get a I/O stat error like this, and you can use explain again and get more information on what happened there. Path scale. Again, I don't think I want to go through these options. I'm not using the path scale compiler anymore, to be honest. Oh yes, there is one thing, however, but it's in another part of the slides that I need to tell you about path scale. In this slide, you can see how different compilers implement the same thing, so it may be useful as a reference. Then there are at least other two programming environments available. So the GNU programming environment and the Intel programming environment. And these are some options that you can find useful for them. I don't have a lot of experience on these two programming environments. But again, man pages are available for both of them. Is the Intel compiler programming environment available at CSCS? Yes? Okay. Yes, there is one thing that you need to know about Intel. To my experience, when you when you compile, when you use OpenMP with Intel compiler, at runtime, you have an extra thread. So you are compiling for 4 OpenMP threads. You get 5 threads running, 5 processes running. Now, this can be a real issue if you try to use CPU affinity. So if you want to pin threads to cores, now this is going to be a problem because you have an extra thread, which means that the extra thread gets to core 0, and then you are left with 4 threads to be pinned to 3 cores, which means that on 1 core you have 2 threads. This is totally inefficient, of course, as you can imagine. So you need to do something about this. I don't know whether Intel is going to take care of this. To my understanding, this is the current situation. There are a few things that you can do. So basically, you can get rid of your affinity. If you don't use affinity, then you have 5 threads working on 4 cores. The extra thread is not going to have a lot of work to do, so that's going to work much better than if you force the affinity. I'll show you, when we talk about AP run, I'll show you which option you have to use to do that. Some general and programming considerations to get efficient codes on the Cray XE6. Memory allocations. Okay, we are using a Linux operating system, so there are features in Linux that make sense on a general Linux box and don't make sense on a Cray machine for many reasons. In particular, the main reasons for which these kind of options don't make sense on the Cray is that because on the Cray you are not sharing the compute nodes. You are the master, you are the only user of the nodes when you run the application. No one else should use these nodes. So all the features that are related to sharing and giving resources back to other possible users are of no use in this situation. So one of these, for example, has to do with the allocation of memory. There are some regions that exist to allow a program to return unused heap space to other possible processes running on the same memory. This feature is not used, is not necessary, it's even harmful on the Cray. So what you'd better do is to set this value to 0. You don't want to have mmap regions, you just need to use one region, you are the only user, you don't want to give heap memory back to anyone else. Another feature is related to memory allocation. It's this threshold, which by default is set to 128 kbytes. And the reason is always the same, to simplify the sharing of the memory with other possible processes. This is not the case. You want a big number here, not a small number. So you should set this variable to this value. These are 2 variables for memory allocation that you'd better try to set in your codes, because the memory allocation and deallocation is much more efficient if you set these numbers rather than if you use the default one, the default Linux ones. The Cray programming environment, I understand, by default sets this variable like I've shown you. Huge pages. Okay, we touched this a bit this morning. As we have seen, the default page is 4 kbytes. Now, if you are using, if you are accessing contiguously big chunks of memory, what you want to do is to have this number to be as large as possible. This reduces the memory overhead, the overhead of thrashing these pages. So what you want to do is to set this number higher than the default. On the processor are available different sizes of memories. You can find information on this intro huge pages man page. And what you have to do this, it's this one. You need to link your code with the right library. Then at runtime, you need to activate the library with this option. When you launch the program in AP-Run, you need to pre-allocate these huge pages that are available on the node. You have two ways of requiring the huge pages, or an advisory mode, or this required mode. If you ask with the advisory mode, what happens is that at runtime, if the pages are available, they are given to your application. If they are not available, you are using default pages, 4K byte pages, and your application continues. The good thing is that you run all the time. The bad thing is that you run, but you don't know whether you are running in an efficient way or in the usual way. So assuming that your application gets benefit from huge pages, in these cases, you don't know whether you have actually got the huge pages or not. So what you can do is to add this extra S here, which is the required mode. In this case, if the huge pages are not available for your application crashes. So it crashes, you don't run the code, but at least you know that it's not running in an inefficient way. Yes?
When you should not use big pages?
You should not use huge pages when you have an application which is addressing the memory in a sparse way. Because if you are jumping, you have indirect addressing in your code, for example, and you are jumping through the memory. Maybe you are jumping through different pages in memory, so every time you touch a page, this page has to be loaded there. So at this time, it's better to have small pages rather than having large pages.
Wouldn't you expect in a normal program both types of memory access to happen?
No. If you have a typical vector algorithm, that will go straight through the memory, and then you'd like it better use huge pages. If you have, say, sparse matrix algorithms, then you're likely to have indirect addressing.
For the numerical part, but for all the overhead that you may have in a program like input parsing.
No. I'm talking about the numerical part. Yes, this affects the way the kernel of your code it's running. Yeah.
Well.
No.
Is your question why can't you choose the granularity based on a module or a?
No, the point is that I want to make. Of course, with this you want to improve efficiency for the numerical part, but you may hit restraints or constraints by, in my opinion, by other parts of the code which are
not numerically intensive.
Which are not numerically intense, which are very scattered around memory, and if you then use huge pages, as you said, your code is going to crash.
Yeah, I mean, I have the assumption that when you use this kind of machines, what you really have, it's a numerically intensive application. But nonetheless, you can try, right? The good thing is that you activate at runtime and see what happens. If it's bad, you don't use it anymore. You have the flexibility to try this. Okay, this is the communication part. You can find in the paper a lot of environment variables. I'm just going to tell you about the basics of this. So there are several environment variables that you can use to control some features in the communication part. There are some environment variables that provide you interesting feedback. So for example, if you set this environment variable, you get all the values that all the other environment variables are set to. So this is useful for logging what you are doing. You run an application with certain environment variables, and you want to record what you are doing, right? Because in a week or in a month, you can get different operating system versions. You can get different MPitch library version, and you can get different default values for the environment variables. That is possible. Or even, if depending on the number of cores you are using, the number of MPI ranks you're using, you can get different values associated to the environment variable. So if you specify this, you get a log of the values of all the environment variables. If you set this MPitch CPU mask display, you cause each MPI rank to print at MPI init time information about which core that MPI rank is pinned to, which core that MPI rank is using. Again, if you have 100,000 MPI ranks, may not be that useful to have 100,000 lines in your code. So you can do this maybe once and then understand what's going on, and if this is what you want, it's okay, you don't ask it anymore. If it's not, you need to understand why it's not what you think it should be. I'll show you an example of this in the lab session. And this is the mPitch max thread safety environment variable that Neil was referring to in the previous talk. You can use this to specify the thread safety level. And the highest level of thread safety is this multiple level. You set this variable to this value. And this is the multiple thread safety level. And in this case, you need also to link to this library at link time. Again, this is exactly what Neil said before. You don't need to change the MPI in it. This takes care of what you should do. I described this morning the different protocols that are available on the mPitch communication. And you have variables that you can use to control what this means. So for example, you use A0 protocol if the message fits in the mailbox, and with this environment variable, and the size of the E0, the size of the mailbox depends on how many MPI ranks you have in your job. MPI rank is a MPI parlance, is MPI way of saying an MPI task. Okay, it's not very meaningful to me, but that's how it works. So depending on how many MPI ranks are in your job, the threshold of the message protocol varies. Okay, you need to know this if you want to fine-tune your application. And again, several variables. This, for example, is the variables that you can use to control the maximum message size, the threshold of the message size that controls the E0 protocol. This is really fine-tuning your communication, right? You have a lot of possibility to fine-tune the communication. And these are some examples of variables. You have that on the paper. They are available on MPI, and you can look at them when you are in a situation where you really want to stress the MPI communication. This, for example, is the threshold that you can set and control whether your communication is implemented in the Gemini FMA or in the Gemini block transfer engine that I told you this morning. You may want to try what happens if you change this threshold, increase or decrease, and see if your communication it's better or not, improves or not. This one is something you want to consider, because in some cases, maybe it's not true anymore today, but in some cases we've got some code crashing at the end of the execution. They were simply or crashing or hanging. The program has completed, has done everything, but it was not exiting, it was still there hanging. By setting this environment variable to disabled, that could be a workaround for this problem. If you find this problem, problems like this, you can try to see what happens setting this variable and see if the problem disappears. Of course, this shouldn't happen. The software should take care of this and should never happen, but in case it still happens, you can try this variable. Then you have a lot of collective MPI functions, and the algorithms that implement these MPI functions are pretty complicated. There are several possibilities in literature. mPitch uses specific algorithms, and for different message sizes, some algorithms are more efficient than others. So there is a threshold that says if the message size, if the size of the variables is lower than that threshold, I want to use this class of algorithms. Otherwise, I want to use another class. You can control the threshold, for example, or you can control the algorithm that is used by several of these MPitch environment variables. Okay, this applies to all gather, this applies to all reduce, and so on. Okay, so the idea is that you should look at the MPI man page. There are a lot of possibilities if you want to fine-tune the communication. I/O. Okay. As I said before, the XE I/O architecture is pretty rich. And you have the compute nodes, you have the I/O nodes, the I/O subsystem is connected to the I/O nodes, and then you have, for example, Luster, which is the parallel file system, high-performance parallel I/O file system that is used on the XE machines. There is a picture here. So you have, for example, the set of login nodes, you have the set of compute nodes, you have the system interconnect, and then you have the I/O nodes here, and the disk attached to these OSS nodes. So your application, okay, you run AP run on the login nodes, then you have the application running on the compute nodes, and then you have some software component. For example, you write a file on the Luster file system. What this does talks to layers in the operating system running on the compute nodes, and through the interconnect, your data is moved to the right I/O node where the Luster OST component is running, and this takes care of the writing of the data on the file system. So when you consider, for example, I/O bandwidth on your application, you should consider all the paths that data should perform going from the memory on your compute node to the physical disk. So the bottleneck may be in the disk bandwidth. In some cases, may even be in the interconnect, or in the bandwidth you need to move data out from the node. Okay? So depending on your configuration, because this can be very fast, and all these disks, for example, can be aggregated to keep data, to keep records for a single file. So a single file can be striped across multiple disks in order to get use of the parallel bandwidth that's available here. But what you can do is to increase the bandwidth here. So if you are writing to, I don't know, 100 of disks, you can do this, a single file to 100 of disks, then likely you are limited by the bandwidth that's available here, rather than the bandwidth that's available on 100 of disk links. And to do this, just what I said, you should have a look, or try to understand what striping, file striping means. What this means is that you can control how files are mapped to OSTs, how files are mapped to disk, basically. You can have you can have one single file striped across a set of disks, and so when you write a large record, you can have blocks that are written on different disks using the different disk channels, and so improving the throughput. There are some recommendations and there are some simple rules you need to be aware of if you want to optimize the I/O performance. So, for example, the first thing that you have to keep in mind is that you are likely not the only user of the I/O subsystem. While you are the only user of the compute partition that you are running, no one else is running that partition. On a large system, you have a lot of applications running at the same time, all of them writing to the I/O file system. So you need to take into consideration that the performance you are seeing may be affected, but by other applications running at the same time on the machine. But assuming you are alone on the system, so weather application, for example, are in this happy situation, you need to understand what's better for your application, and likely what's better is to use as much I/O bandwidth as possible. So to do this, you have a LFS command, and you can use LFS command to set the stripe. You can set a file striped across multiple OSTs. Let me see if I have an example. No, I don't have an example. So basically what you do is to set LFS, set stripe, then you say -c, how many OSTs you want, -c 4, and then the name of the file. And then you have other information that are set by default or that you can control, which is the size of the block that is stored on each disk, on each OST. And once you do that, the striping occurs automatically at runtime on the disk you want. From the system point of view, you see a single file, but that file is stored across multiple disks. So, as I said before, if you want to improve the aggregate performance, you need to use as many OSTs, as many disks as possible. But if there are many clients, many programs writing to many files, then maybe it's not worthwhile doing this, because anyhow, you have a lot of disk accesses coming from different sources, and this is not going to provide you any benefit. If you have many clients, so many, for example, many MPI ranks writing to a single file, then maybe it's worthwhile to stripe, because you have one large file that is distributed across multiple channels, and you have many MPI ranks writing, so maybe they can actually exploit the parallelism in the disk structure. If you have a few clients, again, writing to a few large files, again, maybe it's worthwhile to stripe, okay? So there are some hints that you can use or think about when you have this kind of problem. How many of you have application performing a lot of I/O? Okay. Okay, well, these two don't count, of course. And so you have applications running. Which kind of application is yours? Okay. From a parallel, an MPI program which runs on. Okay, yeah, this is something you may want to think about. Okay, so now let's go into some real examples of what it takes to run an application on the XE6. I'm going to show you how APRun works and which are the options you need to use to run the application. Okay, now you already know everything here. This is the name of the application you need to use to run a parallel application on the XT or XE system. If you don't use this, what you are doing is to run an application on the login node, which is likely not what you want to do. If you look at APRun man pages, there are 15 or 16 examples of what you should do to achieve particular specific goals. So have a look at this man page. The most important parameters on APRun are these three parameters. First of all, there is some terminology that we need to understand. The APRun talks about PEs, processing elements. Okay? If you have an MPI application, a processing element is what executes an MPI task. So an MPI rank, it's a PE, processing element. Okay? So with the option -n, you control how many processing element, how many MPI ranks you want to use. Okay? With the capital N option, you control how many MPI ranks, how many processing elements you want to fit in one node. Okay? So we have seen that one x86 node has 24 cores. You can have the maximum number of MPI ranks you can fit in one node is thus 24. Okay? This is by default. If you don't specify this option, you imply that every MPI ranks runs on one core. It's a pure MPI application, and we are using all the cores available in the node. If you are running a hybrid application which has MPI and OpenMP, the combination of capital N and -D allows you to control how your application runs on a node. Okay? So you can, for example, if you have a four-way OpenMP, if you have 4 threads OpenMP in your MPI application, you need to specify 4, -D4. And then, of course, you are limited in this number because now every MPI ranks is using 4 OpenMP threads. You have 24 cores in the node. The only thing you can do is the maximum number of MPI ranks you can run in this node is 6, because each MPI rank takes 4 cores, because it runs 4 OpenMP threads. Okay? We'll try some examples and see what happens. So, assuming x86 system, 24 cores per node, a pure MPI application which is using all the available cores in the node, the only thing you need to do is to specify -n and the number of MPI ranks. You want to run an MPI application with 100 MPI ranks, you specify -n 100. Now, assume you want to run a pure MPI application, so no OpenMP, but you want to run only one MPI application per node. You don't want an MPI rank on each core. You just want that only one of the 24 cores is busy in that node. You may want to do this for several reasons. The most likely reason you want to do this, or let's say the most likely reason you want to limit the number of MPI ranks in the node is because each MPI rank requires too much memory. And if you had 24 MPI ranks, then the memory would not be enough on the node. You have 32 gigabytes per node. If your MPI application is requiring 2 gigabytes per MPI ranks, then you cannot run more than 16 MPI ranks in that node because you have only 32 gigabytes available. Okay? So if you want to limit this number, you need to use this -n option to do that. Now, if you are running a hybrid MPI OpenMP application, for example, you are running 4 MPI ranks per node. This is exactly the example I told you before. What you want to do is to have 6 MPI ranks per node, each one using 4 OpenMP threads. So what you want to do is to AP run -n4 -d6 and then the number of MPI ranks you are using. If you want the code to be actually parallelized, you need to set the OpenMP environment variable like this. OMP num threads equals to 6. Okay? So this number here, OpenMP num threads, should be the same number that is specified in the option of the AP run command. Clear enough? Yes.
When we say 4 nodes, is it guaranteed that each of them is running on each?
This one?
Yeah, each die gets one MPI process.
Okay.
Is it correct?
If you are using, the way they are distributed is by starting from core 0 and going down. Okay? So if you are using all the cores in the node, by the combination of MPI and OpenMP, you are getting what you expect. If you are using a different number, then you may choose different strategies, because if you are using, for example, only 3 here, but you want 6 here. Okay? So you run 3 MPI ranks with 6 OpenMP threads per MPI ranks. We are using 18 cores out of 24. If you don't specify anything, we are using the first 18 cores, which is not an even distribution of the cores. This is not the most likely, it's not the most performant situation. You would like each MPI ranks to stay on a different die. Okay? So there are AP run options, which I'm going to show you in a moment, that allows you to control what's going on and to get this precise situation. Now the question is, why should you want to use only 3 MPI ranks? That's a different story. But if you had this problem, this would not be a solution of the would not be an efficient solution of the problem, and you need to use other AP run options. And this is what I'm going to explain you now. It's exactly how you map the PEs, so the MPI ranks, to specific cores. And you do this by using the CC option. If you don't do anything, by default you get CC CPU, which is what you expect. So the MPI ranks and the OpenMP threads are pinned to the cores, and they stay there. They start on a core and stay on the same core for all the execution of the application. They don't move around. If you do this with the with an OpenMP code compiled by the Intel compiler, you are going to get into troubles, right? You need to tell AP-Run that he has freedom to move cores, to move threads around. Okay? So you don't want to use this one. You want to use another option, which is NUMA something that we will look at in the man page. Okay? If you compile with PathScale, you need to be aware that the PathScale compiler is trying to set its own affinity policy. And this may conflict with what AP-Run is doing. So what you want to do if you are compiling with PathScale is to disable the PathScale policy and let AP-Run take control of the affinity policy. Okay? So running an OpenMP application compiled by PathScale, you'd better specify this environment variable. Further AP-Run affinity control, there are other options that allows you to fine-tune and control where your application, which cores your application is using. The most useful, well, there are two which are most useful to me, and one is capital S. With this capital S, you control how many PEs are allocated on NUMA nodes. So if you want to have an MPI rank on each die, we have 4 dies, okay? 4 dies each of 6 cores. You should specify here 1, -S1. In this way, only one MPI rank is executed on a single die. So if you had 3 MPI ranks and 6 OpenMP threads, by specifying this, if you have 3 MPI ranks and 4 OpenMP threads, by specifying this, you get the first MPI rank using core 0, 1, 2, 3, the second MPI ranks using the cores on the second die, which would be 6, 7, 8, 9, and the third MPI ranks using the cores on the third die, and the fourth die would be left empty. Another interesting option is this, SS. By this, you force the application to use only the memory that is available on the NUMA node. NUMA node in this sense is the socket, is this die, this 6-core die. So you avoid, by using this option, you avoid one core accessing memory which is allocated on the other node, okay, on the other socket in the node. You are accessing only local memory. You are not using NUMA features. You are accessing only the memory that is closer to where the application is running. Of course, if you do this, you are limited in the size of the available memory to your application.
Would it make sense if I have a pure MPI and no OpenMP to use this -SS option?
If you have a pure MPI application and you are using all the you are running 24 MPI ranks per node, then you have the ranks that run on a certain die access only a certain portion of memory. So I don't know.
If I'm sure that I have sufficient memory
Yeah.
per rank.
Yeah. I mean, this is useful. And okay, let's say this one. This is useful in all cases, but when you don't have enough memory, right? If this is not limiting your memory, the size of your memory you need to access, then I'd better force this option in AP Run. The only reason not to use this is if I don't have enough memory. You can do also some complex things on the XT or XE using AP Run. So for example, you can run 2 applications or 3 applications in this case, sharing the MPI communicator. You can have 2 executables and they can talk together using MPI, but being completely different executables. You can run multiple execution following this multiple program, multiple data kind of programming model and run different applications. So for example, you can have an ocean model here, an atmosphere model here, so 2 completely different codes, and they can still talk together using MPI. Or you can do funny things. For example, you can run you can specify different capital N options in these runs. So you can run an application and have core 0, MPI 0, having access to all the memory in the node, and the other MPI ranks sharing the cores on other nodes, for example. Because if you can set capital N1 here and leave the default here, and so this application is running with only one MPI rank in the node, so MPI rank 0 is accessing the whole of the first node, and all the others are sharing the remaining nodes. So it's very flexible. You can use it for many different purposes. How much? Okay. Last slide with... Now, this is the core specialization that Neil was referring to before. In some cases, the system noise, although the compute node Linux is designed to minimize the effect and interference from the operating system, in some cases, the system noise is significantly affecting the scaling of your application. So what you can do, what AP Run allows you to do, is to say something like, OK, I have 24 cores in my node. I want to use only 23 cores, and I want to leave 1 core without running the application on that core, and that core is free to handle all the operating system interrupts, or whatever the operating system needs to do is performed by this core, and I run my application on the other core. So the application that are running the cores that are running the application are not affected at all and not interrupted by operating system issues. And you can do this by specifying this R option in AP Run. And then there are some details about what you need to do to be sure that the right number of cores is provided to your application, because now you have that 1 core per node is not available to the application. So when you need to compute how many nodes your application requires, you have to perform some computation and understand what's the right number. So AP Run and AP Count allows you to simplify these little computations. Okay, so now, closer to the hands-on lab time, what you need to do on this machine to run a batch application. As I said before, in this application, the batch subsystem is called Slarm. And what you need to do is just set up a batch job like this. You specify, for example, the name of the job. You specify the time you need your job to run, and how many nodes should your application use, number of nodes. Then, for example, in this case, you run a hybrid application on using 6 OpenMP threads, running on 32 MPI ranks. Okay, so this application is actually requiring 32 times 6 cores. And you have already computed that these 32 by 6 cores can fit into 8 nodes. Okay? Of course, you cannot use here, you cannot ask here for more cores than what you have requested in the batch job, because this is the partition that ALPS is giving you. This is for running a batch job. You have another possibility, which is starting an interactive session, which is what I did before. You run this, and you are given an interactive shell, so you can run AP run commands on this shell. And from the system point of view, this is a batch job. Okay? So I don't know what is the limit. There should be a time limit here. This is not the right way of doing things. It's likely the way we do things in this hands-on session. But of course, in a normal batch environment, you want to limit the number of people who are there, allocate 100 nodes, and then go out for lunch, and the nodes stay there allocated, right? You don't want this to happen.
Is there 1 hour limit?
During the day, yes.
Oh, there must be, right?
Yeah.
At night, you can run.
Yes, there is a wonderful web page on CSCS that explains you everything you want to know, and likely more than that, about Slarm. Then, okay, so now we are going to start this hands-on, so you can try to see. Yeah, I mean, in the near future. And once you run the application, you may want to see what's going on. So you may want to check what's going on. So you have some commands that allows you to check this. I've shown you already XT node stat, but you can use also AP stat to check the status of your AP run applications and what they are doing, and if they are alive or not. If you want to have a look at the batch jobs, the QStat, I think it's named QStat also for Slarm, right? Or you have a script that, and you use QStat to check the status of the batch jobs. So the difference between the batch jobs and the AP run applications is that batch jobs are in the batch queue, and likely in one batch job there are 1 or more AP run applications, right? So you're looking at the same thing from different points of view. There is a lot of documentation around. There is also Twitter if you want to go there, but I want to show you, if I can, the beautiful CRAY-doc page. You go here, docs.cray.com, you select in platforms, you select the XE, and you get all the documentation you want about the XE system, and you get also man pages somewhere. Okay, so you get information about the basics, about the programming environment. These are man pages for the programming environment, and you get also information about the libraries and so on, performance tools, and so on. It's a very simple way of getting information. So even if the man page is not available on your system, you can always go on the web and find the man page here. I think it's enough, right? More than enough.